We're talking about how to calculate free energy changes in standard states. Now we're going to look at, well, what if it's not in a standard state? Because free energy changes for standard states is a very specific, narrow set of conditions. And most of the stuff we're going to look at is not in a standard state. So if we look at this process of liquid water going to water in the gas state, the standard change in free energy is positive 8.59 kilojoules per mole. What does that mean about the spontaneity of that process? It's non-spontaneous. And yet, if you spill water on the floor or you mop the floor, does it evaporate? Yeah, of course it does. It is spontaneous, so how does that work? Is water on the floor in a normal room standard state? No, it isn't. Because what's the standard state for a gas? A pressure of 1 atmosphere. The pressure is 1 atmosphere in the room, but the partial pressure of water is much less than 1 atmosphere, right? So ordinary conditions, the partial pressure of water is much less than 1 atmosphere. And so that's going to change delta G for this process. So to predict spontaneity under non-standard conditions, we need to calculate delta G for the reaction. Not the standard change, but just the change, the free energy change under non-standard conditions. And here's the relationship between free energy change and standard free energy change. We're going to add a plus RT natural log of Q. Q is the reaction quotient. Remember, that's the same as an equilibrium constant. But instead of using equilibrium concentrations, you use whatever concentrations are currently present. So Q is the reaction quotient. T is temperature, as frequently is the case, it needs to be in kelvins. And here R is the ideal gas constant with the units of joules per mole Kelvin. So if we're looking at gases, then we would typically use QP, where we're doing it with the pressures as opposed to the concentrations. If we have solutions, we're going to use QC, where it's calculated using concentrations. So let's look at that the reaction between, well, it's not really a reaction. In equilibrium, the transition between liquid and gaseous water. In this equilibrium, the reaction quotient is going to equal the pressure of water, right? Because here's our chemical reaction. And if we were going to calculate Kp for that, it would be the partial pressure of the product over the partial pressure of the reactant. Or you could do it with concentrations. But this is a liquid, and so its concentration or pressure doesn't change. And so Qp is equal to the pressure of the water, okay? So under standard conditions, what is the pressure of water? 1 atmosphere, because that's what a standard condition is. Q is always going to be 1. Well, if we've got our relationship there where delta G reaction equals the standard delta G plus RT natural log of Q, what is the natural log of 1? 0. It's 0. So if this is 0, then delta G equals the standard delta G. Okay? So that's what we've got going on here. Well, I'm sorry. Backtrack. So here we've got Q equals 1. Over here we've got partial pressure of 1 atmosphere. And over here partial pressure of 0. So the x-axis is partial pressure of water. And then free energy increasing as we're going up here. So if Q equals 1, then delta G equals standard delta G. At equilibrium, Q is equal to the equilibrium constant. And the free energy change there is going to be 0. What does it mean when delta G is 0? No change, nothing's happening. That's equilibrium. It's not going forward, it's not going reverse in a net sense, right, overall. It's a dynamic equilibrium, so it's going back and forth, but overall there's no change in concentrations. Over here, with a high pressure of water, we're going to see that the water condenses, right? The vapor condenses into a liquid. This is what happens at night when it gets cold and you get below the dew point and the water just condenses and everything gets wet. It didn't rain, it's just dew that condenses. So if Q is greater than K, we're going to get condensation. If Q is less than K, we're going to have water evaporating. We're going to have a negative delta G, and so this is going to be spontaneous. And this is what's happening in a normal room where the partial pressure of water in the air is less than the equilibrium amount, and the reaction will be spontaneous. Does that make sense? You okay with that? So at 25 degrees Celsius, liquid water is in equilibrium with water vapor at a pressure of 0.0313 atmospheres. And the partial pressure of water for this reaction is Q, right? So if Q equals 0.0313, we can calculate the free energy change for the reaction. Here's the standard free energy change. So delta G is going to be that standard free energy change, kilojoules per mole, plus RT, so 8.314 joules per mole Kelvin. Temperature of 25.00 would be a temperature of 298.15 Kelvin. And then the natural log of Q, 0.0313, ran out of space. What do we have to watch out for? Units. This is kilojoules and this is in joules, okay? So I'm going to turn this into joules. We'll end up turning it back, but it just makes it a lot easier to do on the calculator. So instead of the K there, I'm going to put 10 to the third in the calculator. So I've got 8.59 EE3 plus 8.314 times 298.15 times the natural log of 0.0313 equals, interesting, I come up with 3.03. .830. Let me check my work here. Let's calculate this bit separately. 8.314 times 298.15 times natural log of 0.0313. So this is negative 8586.9 blah, blah, blah. And that would be units of joules per mole. If we convert that to kilojoules, that would be negative 8.59 kilojoules per mole. When I came up with 3 here, that's a very small difference between these large numbers. It is essentially 0. So delta G reaction is 0. This small difference comes about from amount of precision. Any questions? I got this 3 by plugging the whole thing into my calculator. And that would have units of 3 joules per mole, which relative to the 8,590 joules per mole is essentially 0. Yeah, so if I turned it back into kilojoules, it would be 0.003 kilojoules. Very small. Yeah. So this is showing what this comes out to, and so then if let's just kind of, I'm really wishing I hadn't done that. So 8.59 kilojoules per mole plus this negative 8.59 kilojoules per mole is where we get the 0. This is essentially sort of an odd rounding error that it didn't come out to be 0. Any questions? Here's another example. On a dry day, the partial pressure of water is 5 times 10 to the minus third atmospheres. Calculate the free energy change for the reaction. So we need to remember what the standard free energy change was. It was positive 8.59 kilojoules per mole. The equation is delta G is equal to the standard delta G plus RT natural log of Q. And what can kind of mess you up on an exam is, it's like, okay, I remember this, but just what's going on here? They gave me a pressure, I don't know what's going on. And so we have to remember, what are we looking at? We're looking at liquid water going to water in the gas state. And if we were to calculate K for that, it would either be the concentration of water in the gas state, that would be Kc, or for Kp, it would be the pressure, the partial pressure of water in the gas state. The liquid water doesn't come into it because it's a liquid, its concentration doesn't change. So they're saying here's the pressure. The pressure is equal to Q for this situation. So then we've got that positive 8.59 kilojoules per mole plus RT, 8.314 joules per mole Kelvin. They didn't tell us what temperature was.
So it's just asking for anything other than non-standard. So
well, it's non-standard, But what, if you had to assume a temperature, it's on a dry day, there's water, this is the partial pressure, maybe room temperature, which is 25 degrees Celsius, just like the previous problem. So we're going to assume they mean room temperature. And the natural log of Q. So Q is 5.00 times 10 to the minus third. Yes? So the temperature, I probably should have included it in the slide, but I didn't because I was just coming off of doing the previous slide where the temperature was given, and this problem actually goes along with the previous one. But what if you had a problem like this and you weren't given a temperature? Well, sometimes we do have to make assumptions. Make an assumption that's reasonable. So what would be reasonable here would be to assume room temperature, which is 25 degrees Celsius. Okay, so let's not do what I did before. Let's just calculate this separately. So we've got 8.314 times 298.15 times natural log of 5 times 10 to the minus 3. So this is minus 13133, and that would be joules per mole. Over here I've got 8.59 kilojoules per mole. So if I want to put these numbers together, I want to convert this to kilojoules. So what I'm going to do is I'm just going to move the decimal point over 3 places, and that's kilojoules. You can write it all out if you want to. So now we have this negative number added to this positive number. The negative number is larger. And so we're going to end up with delta G being a negative number, 4.54 kilojoules per mole. Is the evaporation of water spontaneous here? Yes, it is. Negative delta G means the reaction's spontaneous. Does water evaporate when the humidity is low? Yes, it does. Any questions? Incidentally, this partial pressure, 0.0313 atmospheres, that is the partial pressure at which the air would be saturated with water at 25 degrees Celsius, and the water would not evaporate. It would just sit there. And it would feel very, very humid. That's essentially 100% humidity. You guys ever been in 100% humidity? You almost feel like you can't breathe. It's just like you're surrounded by a wet blanket. When Dr. K and I got married, it was in Iowa, and it was 95 degrees that day and 95% humidity. It was just miserable. That's why we had wedding inside. Okay, so let's do a real problem here. Consider the reaction at 298 K. We've got H2S reacting with SO2 and forming solid sulfur and water, and we're given delta G, the standard delta G. And we're asked to calculate delta G under these conditions. So we've got partial pressures of the dihydrogen sulfide, the sulfur dioxide, and the water. And then it also asks, is the reaction more or less spontaneous under these conditions than under standard conditions? So this is telling us how spontaneous the reaction is under standard conditions. We'll calculate delta G, and then to answer the question, that last question, we'll have to just compare. So delta G is going to be delta G standard plus RT natural log of Q. What's Q? We have to calculate it. So we're going to look at the balanced chemical equation and ask ourselves, well, what would Kp, the equilibrium constant using pressures, be? Well, it would be the pressure of solid sulfur? No, I don't need that one. The pressure of water squared. All right, so this is pH2O squared, because there's two of them, divided by the pressure of H2S squared times the pressure of SO2. Right? If we plug in these conditions, which are not equilibrium conditions, they're just what it is right now, then Kp, instead of Kp, we've got Q. So we're calculating Qp here. It's the same formula, just not equilibrium. So for the water, I've got 0.0100 squared, and the H2S is 2.00 squared, and the SO2 is 1.50. 0.01 squared divided by 2 squared divided by 1.5. So that's what I'm coming up with for the value of Q. So here I'm going to put in minus 102 kilojoules per mole for delta G0 plus 8.314 joules per mole Kelvin times the temperature, 298 Kelvin, times the natural log of 1.67 times 10 to the minus 5. 8.314 times 298 times natural log 1.67 EE minus 5. So this term is negative 27744 joules per mole. If we convert that to kilojoules, we're going to put a decimal point in here, and that's kilojoules. And then we've got the minus 102 kilojoules per mole. So we've got negative 102 and a negative 27.744. You got a different answer? Okay. I did 1.37. Thank you. I don't know why. Well, the buttons are next to each other. But... Okay, so how about 27253? Yeah. Is that better? So 27253. So minus 129.253. So minus 129 kilojoules per mole. Is it more spontaneous or less spontaneous? It's more because delta G is more negative than it is under standard conditions. Any questions?